In this video, I'm going to go through the process of using row operations to find the determinant of a matrix. I'm using a 3 by 3 matrix as our underlying example, but I do want to point out before I start, you might look at what I do and say, oh, well, I could just use the formula for 3 by 3. It's honestly not that bad. But if we get to a 4 by 4 matrix, a 5 by 5 matrix, or if you think even bigger, if you were trying to program a computer to do this, you're not going to be able to have it use a formula that has n factorial entries. That's unreasonable. So what I'm presenting here, if it looks overly simple, it's just because I wanted to choose as small as possible of an example so that this video doesn't take forever. All right, so how are we going to use row operations to figure out the determinant of a matrix? Well, here's our process. The first thing we're going to do is we're going to row reduce the matrix to echelon form. I said the echelon form, but that's definitely not what I meant to say because there isn't just one echelon form, so let's change that. I want to go just to echelon form. And this is important. I could go all the way to reduced row echelon form, which I think is what I initially typed there, but there's actually no need. So we'll see that. And while I'm doing this, it's going to be really important to keep track of the row operations, and in particular, to make sure we're actually doing elementary row operations. There's this temptation to try to do things that aren't truly elementary row operations, right? But we need to restrict to elementary row operations because we need to know what the determinant corresponding to that matrix multiplication is. If we ever get a row of zeros, we'll stop. That means we have a determinant of 0. And then at the end, once we've gotten to echelon form, we're going to figure out what the row operations did to the determinant, and we're going to work backwards to solve for the determinant of our original matrix. So that's the big picture of what we're doing. Let's just dive right into it. So I'm reducing this to echelon form. The first thing I'm going to do is I can't have a 0 up here, so I'm going to switch row 1 and row 2. Next, I want a 1 for this entry. So I'm going to multiply this by a half. I don't know why I wrote that there. Let's organize this the same way. And when I multiply this by a half, I will get the following matrix. Now I need to get rid of this 3 right here. So I'll add -3 row 1 to row 3. Keep writing this in the wrong spot. I can move that over. And if you haven't done row operations in a little bit, if you've been doing things with software or whatever, this is a good time to review that, to practice. So you could, pause the video. Maybe, I guess I could have said this at the beginning. You could try to do this yourself, right? Take this matrix to echelon form and see whether what you get matches up with what I got. So we'll get a 0 here. That was the whole point. -3 times 4 is -12. So we get a -11 here. And then this 2 is not changed because of that 0. Now I need to get rid of this -9. So I'll divide by -9 or multiply by -1/9. So in my next step, I will do this. I'll get a 1 here and -1/3 here. And then finally, to get rid of this -11, I'm going to add 11 row 2 to row 3. So a bunch of things aren't changed. This is going to become 0, and then I'll have, let's be careful here, I have negative 11 thirds plus 2. So that's negative 11 thirds plus 6 thirds is negative 5 thirds. And I'm in echelon form. I could keep going, but there's actually no point, as we'll see. It doesn't help us at all to go any further. So I've completed step 1. I row reduced the matrix to echelon form. I kept track of the row operations, and I never got a row of zeros. If I had gotten a row of zeros, I just would have stopped. I would have said the determinant 0. This is not an invertible matrix. Now I have to figure out what each row operation did to the determinant. And so what do I mean by that? Well, each of these row operations has a corresponding elementary matrix. And so I'm going to say that this row operation corresponds to the elementary matrix E1. And this row operation corresponds to E2. And this row operation corresponds to E3. I don't want a determinant sign yet. I'm getting ahead of myself. And this row operation corresponds to E4. And this row operation corresponds to E5. And when I say figure out what each of these did to the determinant, what I mean is just figure out what its determinant is. Determinant of E1 is -1. Determinant of E2, right? Because I switched 2 rows. Should be not so fast right here, right? So I switched 2 rows. That's a -1. Multiplying by a row by a constant, the determinant is just that constant. So it's 1/2. Adding a multiple of a row to another row has a determinant of 1. Multiplying a row by a constant, I wrote that wrong, didn't I? The row 2 right there. The determinant is just that constant. And finally, adding a multiple of a row to another row does not change the determinant. Or in other words, the determinant of this elementary matrix is 1. Okay, let's combine this all together. And so I think this is a part that it's really important to write out all of your work, especially early on, because it's really easy to mess these things up if you try to just do it in your head. And it's one of those places where it's really tempting to do it in your head, because if you do this in your head, most of the time it'll work, but then some of the time you'll just get it wrong, and it's honestly just quicker to write it out each time. What did I just do? I just took my matrix A. Let's copy it and paste it. And I performed row operations on that, but row operations we're thinking of as, didn't copy. We're thinking of row operations as left multiplication by a matrix, and a matrix that we know the determinant of. And so one way of thinking about this is that what I did was I applied these row operations. First, I multiplied by E1, and then I multiplied by E2, and then I multiplied by E3, and then E4, and then E5. That's one way of thinking about these row operations. And what I ended up with is this matrix. So go back over this and convince yourself that this is what just happened. I started with this matrix. I first applied E1, then E2, then E3, then E4, then E5, and I got this resulting matrix. And expressed as an equation, this is what we get. And if we want to write that again, we're calling this matrix A. It'll just make it a little bit easier to write this out. We're saying that when we multiply all this by A, This is what we get. And we want to find the determinant of A. So what I'm going to do is I'm going to take the determinant of both sides. And hopefully you're starting to see why I stopped at echelon form. Because on the right-hand side, we have a triangular matrix. I could have kept going, but I really just wanted to get to a point where I knew what the determinant of a matrix was, right? And when I was, for instance, here, I don't know what the determinant of this matrix is. That's not useful. But when I get to here, I now know what the determinant is, so I can stop. That's what happens on the right-hand side. What happens on the left-hand side is that the determinant is multiplicative, and we've always written that as a determinant of a product of two things, but that quickly translates to a product of however many things you want. And so the determinant of this product is the product of the determinants. And we know what all of these determinants are. So the determinant of E5 was 1, E4 was minus 1/9, 1/2 minus 1. So that's 1 times negative 1/9 times 1 times 1/2 times negative 1 times the determinant of A is negative 5/3. And then when we solve for the determinant of A, we get negative 30. So just looking at this again, we reduced to echelon form, keeping track of row operations and making sure they were real row operations. We then figured out what each row operation did to the determinant. Another way of saying that is we figured out the determinant corresponding to each elementary matrix, and then we set up this equation where we solved for the determinant. We row reduced till we got to echelon form, because then we know the determinant. We went back, we said, what are our elementary matrices? What are their determinants? We wrote those all out. We wrote this as a product. We applied the determinant, and then we did some calculations. When I say be careful with writing this out, I think that the place you can make a mistake is that you get this triangular matrix, right? And this number matters in the determinant of A. And you also have all these elementary matrices, and those numbers matter in the determinant of A, but they matter in different ways, in the sense that the determinant of A is the determinant of whatever you end up with divided by the determinants of the elementary matrices. And it's really easy to mess up which is which, right? To divide by one, multiply by the other, and have them not be the right thing. So I think it's really important when you're doing this, especially early on, to actually write out the steps, because it'll ultimately save you time. You'll spend a bit more time, but you won't make mistakes. So you won't have to follow back and try to figure out what you did wrong. But also it'll help give you a sense of what's actually going on. So normally at the end of these videos, I give an explanation of kind of why this all works, but hopefully there's not a whole lot to say here. This works because the determinant is multiplicative, right? Because of this property right here, where I can take the determinant of a product and split it into pieces. That was the whole motivation behind it, right? And so hopefully this isn't some totally mysterious thing. We know the determinants of our elementary matrices. We have a process, row reduction, for figuring out how to write an invertible matrix as a product of elementary matrices. And the fact that the determinant is multiplicative, that all combines together into this process of using row operations to find a determinant.